Okay, YouTube, this is my first video on solving trigonometric equations, and what we're going to do is we're actually going to start by taking a look at some properties of equations with real numbers in the first place before we dig into these three equations down here. But go ahead and take a look up here. It says recall that the solution set, okay, so we're looking for solutions to these things. The solution set to an equation is the set of all numbers for which, when we put the numbers back into the equation, it makes the equation a true or a valid statement. So essentially, if I said, okay, I've got an equation here, 5x plus 7 equals 2x minus 5, and I want to solve it. I'm really looking for an x value that when we plug it in here, we're saying what x value exists that when I plug it into this equation, I get a true statement. And so the thing I want to point out here is this. We have a couple of properties that we tend to rely upon when we talk about solving equations, and one of them is addition, and the other one is the multiplication property. And that just basically says if two things are equal, then if you were to add some third number to both sides, you still have equality, okay? Or if two things are equal, then we can multiply both sides by some number here, c, and still maintain equality, okay? So for solving this, you'll notice that this is kind of like algebra, we have variables on both sides. What this means is we need to get all of our variables on one side. When you say solve, so solve, what we really mean is this, isolate, okay? We want to write this down. Solve and isolate mean the same thing, and isolate is a fancy way of saying get it by itself. So what I'm going to do is I'm going to subtract two x's from both sides. You have to take away the x as well. I say this 2x and this 2x cancel out, and I get 3x's plus 7, and this is equal to negative 5, okay? So we're going to subtract 7 now from both sides. You always undo your addition and subtraction before you undo this multiplication and division up front. But we'd say, okay, well, positive 7, negative 7 leaves us at 3x here, and then negative 5 and negative 7 here, those add up to be negative 12. So now we'll undo our division, and we'll save that for last. So we say x equals negative 12 divided by positive 3 is a negative 4. And again, we say that this is the solution. It's the solution because we isolated x. And last but not least, if we were to plug this back in, which is what I want to do here, if we were to plug this back into the initial statement or sentence, which said this, 5 times x plus 7 equals 2 times x minus 5. Let's go ahead and carry this out and simplify both sides. So I get negative 20 plus a positive 7 on the left. On the right, I get a negative 8 minus a 5. And then simplifying these things, I guess, we would be saying this. Negative 13 is negative 13, which is a valid statement. Okay, so solving trig equations. The one thing I want to point out here is this. These are the three trig equations that we've got listed here. Is that we're looking for an angle. Okay. So you'll notice that in each of these equations, cosine theta equals root 3 over 2, or sine theta equals negative half, or tangent theta equals 1. We're looking for the angle that when I plug it in, I get this to be a true statement. So we're going to be showing some work on these equations and walking through how you do this. But step number one is always this. 1, isolate the trig function. Okay, and by trig function, what I mean is this. I've gotten, say, cosine of theta by itself on one side in this equation here. And all these equations here, I already started off by isolating the trig function. But this is step one. Step number 2 is this. Use inverse trig functions to undo the original trig function. We want to write this down. Okay, so for example, in this first equation here, it says solve the following trig equations for the value of theta, or the angle that makes the equation true, and assume, by the way, that your angle is a number, or an angle, sorry, between 0 and 360 degrees. What this means is we don't have to rotate. Say I have my unit circle up here. We don't have to go over one full rotation and name all of the angles in this case. And I say this is also between 0 and 2 pi if you're doing it in radians. So I've got cosine by itself on the left side. We have cosine theta equals root 3 over 2. This is us showing our work, but we'd say now let's do cosine inverse of the left side, everything on the left side, and we'll do cosine inverse of everything on the right side. So we say cosine inverse of root 3 over 2 from above. Okay, and so what I know is that these two things cancel out, and I'm left with just theta. And it literally says, hey, the angle theta is equal to the cosine inverse of root 3 over 2. So now the important thing about this is what this is asking is really what angle that when you take the cosine of it do you get root 3 over 2 for an answer. And the nice thing about this is, we could just say step 3 is either use the unit circle or reference angles to find the desired angles. And I'm going to write it this way, or solutions. Okay? So that being said, I'm saying, well, cosine. Remember on the unit circle that has a radius of 1, the cosine values are the x values. So what I'm really asking for is, can you go find me the angles that had a positive root 3 over 2 for x? So I notice that this one right here does, root 3 over 2, and that's the angle 30 degrees or pi 6 radians. So we would say theta equals 30 degrees is one of my answers. And as a matter of fact, it's not the only one here. I notice that I'm saying, where's cosine positive root 3 over 2? I notice that I also get positive root 3 over 2 for an x value down here, and that's 330 degrees or 11 pi 6. So we say 330 degrees, and underneath this I also want to write this in radians. So we say pi 6 radians, or 11 of these pi 6 radians. Okay, so let's go ahead and take a look at letter B here. We'll go a little bit quicker. We say sine inverse is already by itself. Let's use inverse sine. So we say sine inverse of everything on the left, which is sine of theta. And we're going to do sine inverse of everything on the right of this equation, which is negative a half. And I say, well, these things cancel out. I'm left with theta equals the angle that when you take the sine of it, you get negative a half. That's how you would read this. The angle that when I take the sine of it, I get negative a half. Let's go ahead and take a look at this here. We say negative a half is my sine value here. So 330 degrees, I notice that looking around the outside of this, my y values, I have a negative a half here as well. So we'd say this angle, or these angles, must have been, these two angles here, 210 degrees, so 210, and 330. Okay, so these are my two solutions, and we can plug these back in and see that we actually get negative a half for our sine values there. Of course we do. And then last but not least, we say tangent is equal to 1. Now, interesting thing about tangent is that we know that tangent by our ratio identity is sine over cosine. So the unit circle does not give us sine or cosine values, or sorry, it does give us sine and cosine values, but it doesn't give us tangent. So to find, where tangent equals 1, we would still say, well, theta is the tangent inverse of positive 1, but we're really saying, hey, what angles could you take the tangent of and get 1 for an answer? And anytime you get a tangent of 1, it must mean that you were dealing with some sort of 45-degree reference angle, because when you take root 2 over 2 divided by root 2 over 2 or divided by itself, you get 1. So we want a positive 1. We say, well, where would I get a positive tangent value? We'd say up here, we'd say root 2 over 2 divided by root 2 over 2. So one of our angles on this last one here is 45 degrees or pi 4 radians. And then our other angle would have to be another place where I'd get a positive 1 for a tangent value. And I noticed that if I were to take a negative root 2 over 2 divided by a negative root 2 over 2, I'd still get a positive 1. So we say this angle is 225 degrees. So you can see how using the unit circle is very helpful in this video, or 5 pi 4s. In the next video, we're going to talk about reference angles as a tool to help us do this. Cheers.